got a new camera, but it seems to make me look fat.
Pitter patter, let's get at her. All right. So last time I showed you some tricks of just dimensional analysis where you take your inputs, make them non-dimensional. We've gone over the full equations for the class, the full Navier Stokes in their most general form. I maybe did a little bit of non-dimensionalization, but this lecture will actually get to actually solving some things. Okay? So, plan for today, right, is I'm going to sort of do some generalized parallel flow problems. Okay? And these are sort of, these are simple incompressible flows, is the name of the lecture, right? So this will kind of introduce you to how sort of non-dimensionalization, or what I call sort of preconditioning, right, will make your problem more general and a lot more simple to solve. And it's like really simple. Like the term of actually finding the velocity field ends up being just like you just look it up in a book, almost trivial. Okay, and then the second part is I'm going to do some Stokes problems, is what they're called. Okay, and this is to introduce you, right, to maybe the first time you'll ever see a dynamic problem in fluids. In undergrad, we never really involve time. We always say steady state. So I want to do these ones because I want to show you sort of transient or a dynamic problem. Right? Essentially not saying this is not equal to 0, which is something you always did in your notes in undergrad. But for this class, I want to show you that you can handle some of these problems, only in a certain scale, which is important. And then the last one we're going to do is something called a scene vortex solution, basically, or the Rayleigh problem. And this is important because this is also a dynamic problem. But this is really critical because this is to introduce you to this concept of similarity, or similarity solutions. And they're great examples because they're some of the simplest ones, and they really kind of get at, if you were trying at the step of preconditioning or non-dimensionalizing your problem, you would almost be forced to look for something like this, besides a little trickery that I want to maybe sort of motivate for a bit. All right, so that's sort of the rule. This is important. This is like the biggest trick in a fluids tool bag, a fluid mechanist tool bag, is using these search for a similarity solution, because it usually goes if you do that. But there's a lot of things about these that are not intuitive. And then again, the dynamics ones, I don't know if you have seen this or not, but right, we're really going to go over maybe the heat equation for that. And then this is almost the most important one, I think, because while you've seen this flow several times, I want to do it in this very structured sort of pretend you don't know anything about the solution and you're just sort of looking for one. You have no idea even how this would shake out. You're starting with the full-on you're starting with the full-on Navier Stokes equations, and you're trying to get at what that velocity field is. Now we know what this solution is, right? You've seen these. It's really this Colette and, right, we're just going to look at those solutions. And you did them in undergrad where you had this quadratic velocity profile. And then you maybe did this one where you looked at sort of a plate dragging across a still fluid where you drag a plate across and you just a shear-induced flow. That's the Colette and then Poiseuille flow. I already know I butchered my advisor gets at me that I never say these names correctly, and I'm sorry about that, but to me, they're just the classic examples. I apologize if someone is French and I'm not saying that. My wife speaks fluent French, and she always bugs me about it as well, but you've seen these as the point, and I just want to do it in this extremely sort of discovery way, where all we have right now are these general equations and this idea of like non-dimensionalizing a differential equation. And then I'd want to get there that way, because that can help you with the research, I think, for this paper you're going to write. The idea of starting from just the full-on, putting your scales in and see what simple system you get is important. Okay, an idea I kind of want to get out here is this is called I've named this lecture sort of simple incompressible flows. I'm not trying to be mean here or like, braggadocious with this word, incompressible, but mainly this one. I don't want to, what I mean by simple, it's something sort of, it's a specific meaning where simple has the meaning, right, that we can write down that velocity field. Right? We can explicitly write it down as an equation, as a formula. Right? Not even, right? And then even, so, and this is in the case of sort of explicit or even implicit. Right? I don't think we even have an implicit one for this, but that I consider sort of simple because however you reduce the Navier Stokes equations, in the end, you can actually write down what that velocity field is. It's a pretty simple vector field, but you still won, right? And it still tells you things. And then this idea of the incompressible, we'll see it has a more precise meaning. Sort of really, right? And this kind of wowed me the first time I saw it because I had always sort of done the same thing when I think about an incompressible fluid where I just go, the density is constant. And that ends up being like a who cares statement. It's not even true ever. So there's a far better a way to conclude that your flow is incompressible, right? And mainly this idea that incompressible is not a statement about the fluid property. Okay? So incompressible, right? It's a statement about the flow, right? It's not a statement about the fluid, right? I mean, really, it's kind of both, but you'll see that it's kind of a combination. But really, the driving thing is that incompressibility is not a statement about the fluid or the media that's flowing. It's a statement about the actual flow occurring. And maybe some of you know exactly what ratio I'm talking about, but let's get there. Okay, another key important thing, and this is sort of just, I like this, I do a bunch of math, but, right, we have these set of equations, the Navier Stokes equations, right? So there's the Navier Stokes equations, I'll call them NS, right? And they eat vector fields, rho, pressure, and temperature, okay? And imagine you have some set that is all of the solutions to this equation, right? Now this is abstract, but I'm just trying to reason what my motivation myself of studying these simple examples, right? And that's the idea that if this is the entire set, some people actually think they know what it is. That's unclear, right? So this is a special notation for the set of your region of fluid and then all the functions that would maybe satisfy the Navier Stokes equations. Most of what we're doing is this very, very tiny subset that lives in here. Okay? So maybe we'll call this S prime, the set S prime of these solutions. Right? And it's a very tiny subset, right? Because there's so many assumptions we've put on the Navier Stokes equations that so few of these solutions actually satisfy the conditions. So we're studying a very, very tiny subset of all the solutions in Navier Stokes equations, but right, in an intuitive sort of if you see enough of these things, you realize that if you just take all of these solutions, you really can almost map them out to the rest of the set, right? And that is just a total not mathematically proven at all statement I just made, but I'm just getting at that I think it's critical because there's for all the solutions of the Navier Stokes equations, however crazy geometry you can get, I can study this small set and I can maybe scale up the solution or at least infer things about that solution to maybe understand all of the solutions of Navier Stokes equations. That's a big statement, but right, in reality, you'll kind of see if you're in this world long enough that it ends up working that way. So maybe a motivation, just bang for buck, why on earth you should still study these extremely pedantic, simple problems. Because of that. That's what I think about. That's why I go, you know, I'm not just going to always do a direct numerical simulation, because most bang for buck, I study a very tiny subset of all the solutions to the governing equations of fluid, and then I just map them over, and usually this is done by a scaling. Something like that. Can you see this stuff? I got a new camera, by the way, so I hope it works. It's HD, so hopefully you can zoom in on the camera. Okay, so let's begin there. Okay, so the problem I want to first look at is a thin slot, right, of fluid driven by maybe some pressure gradient, maybe not. Okay, so we'll have maybe this 3D situation. Maybe even, let's say, so this would be a solid boundary, let's say. And I maybe want to have this go on and on and on and on and on. Okay? Okay, and this would go on this way as well. So this is a boundary as well. Right? And this is the top of the plate. Maybe right? So there's solid boundaries in this slot. And however I make a pressure gradient, I'm just saying that I am going to have one. So at the inlet, there's, let's say, a pressure in. And that pressure could come from gravitational pressure, right? It could just be a tank of water or some fluid with an outlet that looks like a very thin sheet, and then it goes into something else that would be driving some sort of pressure. And then on the outside, wherever that goes, far, far away, is some outlet pressure. Okay? So maybe if we think about how we've formulated these things, what would we first think? Well, if we're going to study this problem, right, what's a coordinate system? Okay? So this is sort of this, just, well, this is the one I'm going to pick, right? So I'll make sort of downstream in this direction. I'll have be the x coordinate. So I'm doing Cartesian for this, essentially, right? So that's my coordinate system. Okay? Notice that some sort of notes, right? Just of how I've mentioned this, that x will be in the direction of the pressure gradient. Maybe not in the direction, actually anti-parallel, but it's parallel to where there is a pressure gradient. Okay, this is some sort of wall. The top is bounded. Now, right, we already did this before. Now let's start thinking. How am I doing time? Okay. Okay. So now let's start thinking about the region of fluid I'm then talking about. All right. So the region of fluid, I'll say, starts here and then goes on all the way that way and then maybe all the way in here, right? So again, we can have this sort of, okay, well, if this is if the interior of this thing is my region of fluid, capital omega, I reserve v for velocity, which is why I use omega. Okay, so then what is this? How would we define all the points of the fluid we're trying to consider? Again, this seems way overkill. What I kind of just, I did this for myself even to just kind of see, could I really just not know what these solutions are and maybe get to it through like this, just going around? So if this is the y direction, oh man. Okay, so imagine this is important. I want the y0 to start at the base of there. It doesn't really matter, but I don't want to carry negatives around. Okay, so y is at the base. So this is all the points x, y, and z. All right, and we have right here. So we have y. And then there's this question of the z's and the x coordinates. Okay? So then for the x coordinate, I'm saying that I go from 0, x, all the way up to some length of travel. I don't really know where it ends, but say you could measure the distance of this very thin parallel slot. Okay? And then in the z direction, which is this side, sort of the width of my parallel slot, I'll have another length scale, denote W. Okay? All I've done is I've just told myself, okay, what are the dimensions of the flow I'm trying to model? I haven't even said anything really about this fully developed thing. And it ends up, you'll see it goes away, and it's a different situation you have to analyze. Okay? And then now, maybe we put some conditions on these length scales. Okay? I mean, this is just defining where these points lie for this region of fluid. But maybe some other things, sort of maybe let's say another such that for this point, every point of the fluid must obey something. And really, I'm now going to start making conditions on these defined scales of the problem. I could take a tape measure and I could measure the 2D slot, so we can have some situations there. Okay, one of them being, so you could have H, say much, much less than 1. That makes sense because this is a very tiny number, and then the distance it travels is very, very large. So I could take the ratio of these two values, and I'm just saying that this non-dimensional number has to be much, much less than 1. And then another one another one that's important is I want to then say, I'm really saying this to get a 2D approximation. You then would say, actually when I measured the length and the width was enormous. It was very large. So then, likewise, you also have the case, this. Okay? So, think about, so this means that H compared to W is even less of a number. And this is just, and you can imagine these situations if you just think about fluid falling down, like a thin film maybe flowing down a rooftop. It's not a solid boundary, but it's kind of the same idea, If you had some sort of roof like this, and rain was coming down, it would collect, and then there would be some accumulation that occurs maybe around here, and then would develop into maybe a thin film of fluid that's going down your roof, You zoom in, you get this height h of the actual liquid flowing down. And then those dimensions I'm mentioning are really this L down the roof, So that would be, let's say, this dimension, and then the width being this, So how long is how long is the house? So if you're very, very rich, maybe this is an enormous number and you have 18 bedrooms, so that would hold. So maybe just some justifications on why on earth you would make these statements. And I love just thinking about that all I've done so far is just define, let's say, the volume and what fluid I actually have, and I've already made some interesting statements. I'm just comparing what my tape measure said. Okay, for this whole lecture, actually, how I'm doing this, you can do the exact same thing, except wrap the z dimension all around itself. Okay? So the extra credit for this whole lecture I want you to do it all in cylindrical coordinates. And that makes sense sort of because the length of travel, would now be, let's say you make x the cylindrical coordinate of z down the stream. And then your y will end up, the y coordinate will end up being the radial coordinate in that system. And then you get this idea of you wrap one dimension all around itself, there's a symmetry, and that's essentially taking this thin film, It's taking my problem, which I'm formulating like this, where if this is going into the fluid, so the x is being fluid into the flow, radially essentially is just doing, you're wrapping the problem up around itself. Okay? So, already you should see there's a connection between this idea that I have these infinite large scales, essentially is what I'm saying in the 2D situation. But in the radial situation, you don't have to actually even make these statements because there's a symmetry in the problem. So this is a bit more tricky. But in the radial system, you'll see there's no swirl velocity in some of these assumptions, so it works out even easier. That's the pipe flow thing. right? And even, I should draw this, it's kind of neat too, actually, where this would be, right, a lubricated journal bearing, right, where there's fluid in between here. If this was solid, so there's a surface and surface. And then the hard part is then you're limiting R to 0 to recover this solution I'm talking about. Okay, just a little aside, but that's the extra credit for this one. I like it a lot. Okay, so another thing this actually also implies, which is important, right, is that right, is this, which will be important, right? The sum of 1 over all these heights, you'll just pop back this 1 over h. Why? Because these lengths are enormous. So, right, you can just see that if you put numerical numbers in here, that this sum of 1 over length dimensions ends up being basically, right, a 1 over h, right? In the advanced versions, it really ends up being a 1 over h plus an epsilon because these numbers are very small, and that's what we use to go a little bit further in an analysis. But we're not there yet, so we'll actually just say it equals 1 over h, right? The easiest analysis is always to say some coordinate limits to infinity so you make something actually 0. But you can never do that. OK, 20 minutes. OK, so now that's just the coordinate system setup. OK, so now I want to talk about motion. OK, so motion is prescribed by my Navier Stokes equations. Right, and I wrote all of them out. And we sort of want to get a sense of, OK, how can I start attacking these problems? So one thing we'll do is we'll think about the incompressibility condition, and we'll get there. And we're going to combine the equation of state. So right, there's all those equations involved in here. So we're going to use that equation of state plus a continuity. We're going to non-dimensionalize those to realize that you can make a simplification of the divergence of the vector field if the velocity is pretty slow through here. So then you get the second physical interpretation on this type of flow, which that is you're making some type of model and you've done sort of some experiment where you've measured, I don't care how you really did it, but you maybe probed it for some velocities here and there, and you've maybe measured an actual velocity. So you have some maybe number to go off of. 0.5 meters per second, right? 0.01 meters per second, however you want to do it. But let's say you've done this. So this is important for this when you talk about non-dimensionalization when you use a velocity scale to maybe use this first, right? So the equation of state we had in that general problem was this pressure, right? You can write it in this form too, is that pressure is a function of density and of temperature, right? And keeping in mind that I'm saying still that the density, that the density is a field, and my temperature is a field as well, meaning it's a function of x, y, z, and t. This is a function of x, y, z, and t. So these inputs are still, this is a field, and then a function. OK? And now, and what we say for, right, we said for conservation of mass this, right, that the material derivative of the density field with respect to time, or just that's what the material derivative is, right, is balances, right, the material, right, scaling up the divergence of the vector field by the density field itself. That's the full on. This hasn't made a statement about incompressibility yet. But let's use these two equations to make some statement about when am I really incompressible. And it's not that hard, right? And one thing you do is just you go, OK, well, if this is the incompressibility condition, I want to start talking about, right, rates of change. OK? So to do rates of change, what we're going to do is just take the material derivative of this equation's left-hand side. And then on this hand side, you do the right, you just use multivariable calculus and you do chain rules. Again, I've always stated, right, if in your grab bag of math tools, remember the chain rule and product rule. Because it allows you to just do this reasoning type stuff, OK? So then I have Sorry, silence is terrible in these lectures. I rewatched them and I was just like, oh my God, always say something. Keep talking, keep talking. All right, so this is just, right, I've just taken the linear superposition of variations of both of the inputs, right? And keep them, right, and you could write out the components and see, right, that this operation is still, right, defined because each of these is a field. So if I take the time rate of change of this input, I still have the material derivative, right? Because this material derivative was defined because there was a velocity field. So it still plays nice with just that operation, right? Okay, so I want to now use my equation of state and relate it back to my continuity equation. So now you just, right, we're going to rearrange things. So now I would solve this for this variable. Okay, so I'm going to move this over. Boom. All right, so this, move this over to here. Sorry, I've done it. Do this. Okay, moving it over to here. I have the dt. There we go. Sorry. All right, so I moved this over and I did this division by this coefficient in front of there to single out this capital D material derivative D. Okay, and now what you do is you actually divide the entire equation by a 1 over rho. And you divide the entire equation by 1 over a rho because what that allows you to do is to actually flip this as if it were a fraction. You don't need to worry about it too much. I kind of enjoy thinking about what these conditions are, and these are just smoothness conditions here. And then you come up with this is equal to all right, and this is the relationship that we want. I don't like that. So this relationship is important because now what I've done by combining information from the equation of state and incompressibility is now I have a way to compare now, right, what the change of density in terms of velocity fluctuations, and then a change in density or relative change in density is compared to thermodynamic variations in the field. Right? There's a stark difference, let's say, between these two things. Yes, I know that the ddt is involved, has a velocity field in it, but you have to think about how these really govern the size of the right-hand side. So these are thermodynamic functions, and we now just label them alpha and a beta. Right? And this is that's a thermal expansion coefficient, and then this other one, right, was a 1 over, and it's a change in density with respect to pressure. Right, so this is I think a bulk expansion, volume expansion coefficient. It has like a bunch of names. Alpha usually ends up being small and extremely tiny for the simple fact that, right, if alpha is 1 over a density with change in density with respect to pressure, you need a lot of pressure to change fluids. Not so much with gas. I think it's a compressibility coefficient. Either way, set up, and you just have this important relationship that now I have, right, change in density field and then the momentum change in density field. Right? I mean, in reality, I now move this over, and I actually have the exact same thing. right? I mean, I just divided by this. So now I'm comparing the exact same type of situations. Now, you could equate these two things, and you would get stuck. But really what's important is now taking this form and making all of the equations non-dimensional. OK? So when we do that, we have to pick some scales for the full Navier Stokes equations. Let me just list these out. So all I've done really is I've just reworked my equation of state to use infrared to just look at it in a variational form, where I look at variations in density and variations in temperature. And I just have defined, trickily, these new thermodynamic coefficients. Why have I defined thermodynamic coefficients? Well, it ends up that thermodynamic properties are fairly easy to measure. So you can get further in like making a statement about big or small, because those experiments end up being easier. So I'll have I'll have x, y, and z maybe. We could have them scale as a length. Okay, time, I'll say we'll scale as that length divided by a reference velocity that maybe had been measured. Can you see this stuff? Okay, that maybe has been measured. Okay, and then my velocity vector itself, well, I'll scale that by the scalar value that is maybe like the most seen velocity in the problem. Even these functions I can even scale, because they could have variations, but I could take an average of them. Remember when we had the temperature equation, a k popped up because of heat transfer by the first law of thermodynamics. Cp also popped up, so even if that had a variation, I could take an average. Even letting viscosity vary. I could have the viscosity, if it varied over the field, I could take an average over the entire field. And then gravity, you do this thing where you have L over u squared. So these are all the scales. And then something else is you need to pick a pressure scale. So for a pressure to scale like something, you have to make almost a selection. Now, if I want to retain, this left-hand side of the Navier Stokes equations, when you do this non-dimensionalization, not that hard, I say you just do it, right? Use the definition of this. You get this squared velocity in front. And that's because of how I've scaled the time and how I've scaled the velocity. So in both of those terms, that will pop out. So when dividing that, if you want to retain that, a good way is using that, dynamic pressure, It's a rho u squared, So it's a kinetic energy, So think of it as a kinetic energy even. Or a kinetic energy per unit volume, yeah. So that's one way to think about that is you're retaining that high energy of the flow if you scale pressure by that. And doing that, you will then get the full non-dimensional form of all the equations. In the notes I have it, but let's just have the actual equation of state now written variationally. That ends up being where again, a star means that the variable is non-dimensional. Minus a Prandtl number pops up because of how you actually would scale temperature. For an A, capital dt d star, parentheses. Okay, so now I have a non-dimensional form. It doesn't matter any of the scales involved, If you have the scales that you have now measured, this is a non-dimensional term. So this is an extremely general format because it doesn't care about the dimensions that you have. And then I have terms in there that are redefined, because redefining things is always important to make your math look pretty, What is the Mach number? The Mach number pops up because of this d rho dp, So Mach number is a velocity scale divided by c. Now what's c? C squared is this. There's a change in pressure with respect to the density, and that ends up being the speed of sound within the media. And you would get that through a wave equation, but We're not there yet, right? And then you have an A being this alpha naught, rho naught, Cp naught, even a reference temperature. B is a average of that thermal expansion temperature, and then write your reference temperature there. Prandtl number is what you just saw in heat transfer. And then what else do we have? Oh, yes. And this is just as you remembered it before, where you have this being equal to naught and then a CV rho. Right? This is actually this is a ratio of entropies is the gamma naught. All right? Biggest conclusion you learn is just what I had said before, that incompressibility is not a statement about the fluid. It's not about the statement about the media. It's a statement about the flow, right? Because this is what's driving the right-hand side, the Mach number, okay? If your velocity is much less than the speed of sound within that media, now for a solid, that velocity is enormous. For a liquid, it's still pretty big. And then for a gas, attainable. That's why you have to worry about it. But even still, if it's a gas, if it's slow enough, right, the speed of sound in air is like on the order of 300 something per second, right? What is it, 300 meters per second? 327 meters per second. Either way, it's achievable, but if you have slow-moving gas, right, that still makes this number extremely small. Right? Think about that there's a square in front of there, right? So if you're going half as fast as the speed of sound, that drops this down now to 0.25, still pretty tiny. If you're going a quarter of the speed of sound, it has that square relationship where it kills off pretty quickly. Again now, when you do a non-dimensionalization, any term with a star in it, I write these stars because it reminds me that that basically can be treated like the number 1. So some people drop star notation and just say, I'll just remember it. But I like star notation for non-dimensional things because when I see it then back in my equation, I just tell myself this. Right? And it's not exact. It's not exact at all. But in terms of like the general variation of this differential equation, you're seeing that you're making it a function of parameters, not of the derivative terms in there. Very important to make conclusions about stuff. Because again, you now have these cases to study where most of the time, if the velocity is extremely small or just small compared to the speed of sound within that medium, this becomes then 0. Right? I mean, it's really if Mach squared becomes 0. So it's extremely sensitive. But it could be not 0, right, in other cases, right? So you could just kind of say, well, I mean, the Mach number is sort of just a tiny number, like 0.1 or 0.3, then I can't ignore it. And then there's also this issue of this coefficient right here, which was a function of a thermal expansion coefficient and, right, of a volume expansion coefficient. Right? So now these things, right now this ratio dominates. Prandtl number is always about 1. That can't be too crazy actually when it comes to our analysis, because you look at the Prandtl numbers for any fluids that you have, and they end up being pretty basically around 1. So then it really becomes a function of these two those two thermodynamic coefficients, which you then can measure and then say this number is really tiny. Or it could be really large, and then you would have to consider this. This number is also pretty small for a liquid as well. So, interesting, right? For whatever problem I wrote down, I measured some velocities u, and it's just as simple as seeing that like that. Maybe I look up the speed of sound of speed of sound in water and take my little ratio. I realize that it's 0.0001. I go, it's probably going to be 0. And then you look at this ratio, you look up the property beta, you look up the property alpha. I wouldn't even really care about these or the Prandtl number. Look at that ratio, ends up being 0.001 as well. And you go like, oh man, so that's great. That means basically this right-hand side is 0. Again, incompressibility is a statement about the flow character, not about the media. I mean, it really is, but like you can't just say the rho is constant. Rho can never be actually constant. There'll be some variations. Even in a solid density, we'll have a variation. You could have a dislocation somewhere, right? So this is a better way to think about this, and you can always make a statement about this. Right? Mach number is really always small when it comes to a liquid because of two things. This is hard to achieve, and then these values, and then that ratio is always small for a liquid. Okay, because the thermal expansion coefficient definitely is bigger than the definitely is bigger than this parameter, or the other way around. But the ratio ends up also being extremely tiny. Okay, so there you go, and that's what the incompressibility condition is. It's not that, right? It's it's the idea that this term is actually 0, and it's 0 non-dimensionally, right? Where this gradient is actually a non-dimensional gradient operator. So sometimes maybe before what you had done is you saw that the incompressibility condition is written like this. So sometimes maybe you've seen this, and all this is doing is undoing the product rule in this part right here. So maybe before you had said, OK, my rho is constant. I'm just going to say the entire field is some constant number. That goes away. I can factor that out, and then I get this conclusion. But what I'm saying is it's nice to do this actual exercise of using your equation of state and continuity to see that you can make conclusions about the flow character and what incompressibility actually is. So from now on out, I want you to even think about that. Right? And then better, if this isn't, right, if this is not 0, right, if it's actually just some tiny number, if you go back to how I wrote the Navier Stokes equations before at the end of that lecture, I had this term pop up everywhere. You saw this, right? You saw this term pop up in all the equations to the right of the dv/dt. So if you even have this relationship where you see that this is probably just some small number, then you even could do maybe a small analysis on just putting that epsilon throughout that momentum equation to get somewhere. OK, now we're done with that. So now I've really sort of shown you what incompressibility is. It's a statement about how fast the fluid is going, and somewhat a statement about the fluid properties. But they end up not being that important compared to that Mach number squared. OK? So now let's look at just that full non-dimensionalized Navier Stokes equation. What do we have there? So now, with incompressibility stated, okay, it's a Freud number. What a Freud number is. What do I have a Freud number as? I forget. And then you have a Freud number there, which is a measure of when should I really care about gravity, right? So this is squared. Okay. So this is really, right, this is the general Navier Stokes, incompressible Navier Stokes equation. If it had dimensions, and I put the dimensions back in there, it looks like this. All right, and then along with conservation of mass. So this is dimensional, non-dimensional. This, right? If you don't remember anything from this class, right? If you don't watch any of the lectures and maybe you just happen to watch just this one, this is all I want you to really get away from this class, is how to rattle this thing off really quickly at a conference, and then how to insert some scales probably into what the operations are to make some conclusions about a flow. Everything else I think is just something you'll do once in your life and then immediately forget. What I would like you to do always is be able to write this down on a piece of scratch paper whenever you're sitting down and listening to someone talk about fluids, incompressible. really, the full one helps if someone's talking about a compressible flow. But really write this down and even be able to scale each of the term in there to say something. That's what's important. Okay? So next, I should just keep that on the board. OK, I will keep that on the board. So we have the non-dimensional equation that we'll have, right? And I want to keep it non-dimensional. Those are the incompressible non-dimensional Navier Stokes equations. Again, maybe have that image of this 2D parallel plate flow that we have. I'm still solving this, right? I'm still solving that picture where I had a rectangular plate. Maybe at home if you're doing it in the radial coordinate. But all we haven't got here is this general statement of whatever the dimensions I have, that's what it looks like. Okay? So now I want to get into then this thing. What is this non-dimensional operator? How do I use this? Right? Even this is defined using it too, right? So better get good at using it. Right? So, right, even the material derivative, it's implicitly in there as well. This non-dimensional gradient operator. Okay, so let's go into and really think about what that is. Well, the gradient operator is this, right? It's a row or column vector. Right? It's a column vector of derivative operators. So just as you would do before, right? Well, then if I have an x scaling as an L, a y scaling as a H, and then a z scaling as a W, right? I do my same trick where I insert these in there. Right, so now my x is an L. Boom, and then here I'd have, this is going to be an H, Y star. And this is a W, Z star. Right? All I've done is just this substitution to keep the same idea of I've defined my gradient operator as this row vector that operates on things, and now I've just non-dimensionalized it by just the simple process of substitution. So then with here you go, well, how can I recover this and just write something in terms of the non-dimensional gradient operator, right? I'd like to write something, right, that's just has this thing without that in there. And then you can go, well, I can write a matrix actually, right? I have this 1 over, I'll have a 1 over L, 1 over H. And then I can have it pop up here. Right? Where this is, right, that non-dimensional gradient operator. So you have this sort of transformation that happens to the gradient operator defined in terms of it. So I call that a matrix capital L. Right? And now do you see why I made that, where you make that condition of this sum of 1 over the lengths is basically one of them, right? Because then I do a little more trickery, right, with this product. So I factor out the trace of this, right? So let me call this, maybe this capital L, right? Factor out the trace. I won't have room for this. Right? So this is a matrix, right, that takes this row, right? This is a 3, 1, 3 by 3, and then a 3 by 1. So I get back the row. Yes. So now you just do this trace trickery, right? The trace is the sum of the diagonals because these are all 0. So these are all 0. And then I have a new matrix where I have 1 over H plus L over W, 1 plus okay. And this is sort of a nice, right, this allows you to sort of, right, select out and pick out terms, because this thing is going to be a 1 over h, just because of how we define the scale of the problem that we had originally. If you're lost at where you are right now, it's just sort of, again, I'm just trying to get at some things, and I'm just trying to show that like you just have no idea where to go with this type of problem. So you're starting from the ground basics. And then this operation, right, now what this thing is going to do, right, so I have a way to define this, 1 over h, because the scales ended up being pretty small for the other one. And now what this thing ends up being, right, think about these terms right here. This is, right, this number looks almost like 1 because I have h divided by a very tiny number and h divided by another very, very, very tiny number. So this will really look like 1 over 1 because you could think of these two as 0. Right, remember that like h over L, right, h over L and then h over W were very, very small. So then sort of you look at these things, what you end up getting is this. I have this epsilon 1 epsilon. Okay, oh, this actually. Okay, still makes sense with the units too. All I've done is I've just said, well, right, non-dimensional, non-dimensional, all the dimension encapsulated in here, right? So the gradient being this, and my smallest one was h, so you're still recovering basically what you would usually think of doing. So really quickly, if you see a gradient operator, it kind of tells you, well, I'll just take 1 over the smallest scale, and that can scale that gradient operator for me. But this, you see, there's other stuff that you missed out on. You had the non-dimensional gradient operator, and then you have this, right, this matrix that really picks out, tells you what's small and what's not. Time. Okay. Just moving along. May seem like I'm slow, but everything will crumble. Okay. So now you have a way just from this now non-dimensional operator to make a statement using the incompressibility assumption, which I like. Okay, 2. So just using the thing, right, the h doesn't matter because you have a 0 on the other end, but you can put it there as well. Right? So I have a 1 over h, right? And then after you do that matrix and row multiplication, you get an epsilon, not a 3. You get an epsilon plus right? Now plus. Right? And this is going to now be dotted with this vector right here. Okay, so if it's 0, I can get rid of the h, and then you have this nice sort of compact conclusion that we usually see, and that is I have this epsilon term So you make a pretty standard conclusion here, right? Because as now, if I say epsilon is equal to 0, so if my length scales actually go to 0, I have the conclusion, right, that this term is equal to 0. And again, we're not there yet, but it's good to think about something never actually equaling 0, because 0 and infinity truly don't exist. I just read that. That doesn't give me a bunch of hate. But right, if you have this, it's epsilon here. Now I can say like how it's almost 0, right? Or like how I can say 1 over epsilon is almost infinity. And that's way better. That's way more precise. But for now, I could limit epsilon to 0, and then I get this classical slot flow conclusion. Right? And what does this say? This says that the velocity in the y direction has to be a constant value. I've already made a constriction on this based on the length scales of this 2D problem. Okay, now I have my little picture I want to draw for you. And this is the idea of what I'm doing right now is this sort of scaling and then, right, is this issue of scaling and then making conclusions. But this falls in this issue, right, of that for all fluid problems, what you're really doing analytically, not CFD-wise, right? We're not just doing a direct. If you do a direct numerical simulation of Navier Stokes, what you end up doing is you solve all of those large equations and then look at the numerical errors that pop up and try to quantify those or have it converge better, et cetera, et cetera. Okay, but for our purposes, really the goal of like fluid analysis is making a simplification of the Navier Stokes equations, right? And what does this, right, right, and a way to do this, right, a methodology to do this is to look at the scales of the problem, and that will infer what the simplification actually will be. That's what I've done here, right? I just drew the geometry, and then I made epsilons and looked at length scales and saw that things get canceled out or things had to be very, very small, right? Okay? But it also can actually go the other way, right? You could just simplify the Navier Stokes equations and then do a non-dimensional form of the simplified equation that you have. So they kind of inform one or the other, which is just some sort of play around thing that you have to do, right? So if you have here and then you do it to scales non-dimensionalization, you sort of can tweak the scales of your simplification, right? So this process going in this direction is you just look at the Navier Stokes equations and then you just arbitrarily say, I don't think that term matters, I don't think that term matters, and I don't think that term matters. And then you get a dimensional equation and then you non-dimensionalize. But you can go the reverse way too, right? You can start off with scales based on the problem and then go to your simplified Navier Stokes equations with that non-dimensional form. And that will simplify it for you, right? But it's a circular process, right, because you can kind of keep going, right? Because if you simplify, get scales, you can find new scales and then find more solvable problems, right? If you non-dimensionalize first, it's just a math problem, right? There's no dimensions kept up in it. You have like derivatives equaling 1, et cetera. So this is sort of, if you do it this way, you find new problems, right? If you're looking at the non-dimensional station, this lets you find new problems, right? And what goes into this process of scales and non-dimensionalization? You've probably seen already, right? Well, the biggest one that we've used right? I've only made statements about H, L, and W. So geometry is a big one. A time scale is also a big one, right? And they are sort of, right, and they are linked, but they are independent as well, right? You have geometry and you have time, in space-time. Okay. And then you also have this pressure scale. I should say for the incompressible Navier Stokes equations. Okay? So this is informing scales and non-dimensionalization. And you could also say it's also, right, it could also just immediately inform the simplification. These are what you have at your, these are what you first have if you don't know anything about your problem. You at least can measure some dimensions. You can at least think about, am I taking my time away in seconds, years, minutes, et cetera? Okay, not an hour. I can do this. And then there's this very difficult problem of a pressure scale, I think. Right? I think this trips a lot of people up. Okay, another thing I want to say with this simplification, the output of this process of simplifying Navier Stokes equations is right, is after making it non-dimensional, so you go back around and make it non-dimensional, is getting terms like an epsilon, keeping them or letting them go to 0. Right? That's the goal of this, is you get some sort of small or tiny parameters, and then you can just say it's 0. Not arbitrarily. The advanced version being it's not actually 0, you keep it around, then we do something called an asymptotic solution. But we're not there yet. And then, there's even something that now has to inform this situation, right? And this is sort of, and I name this, this is where you can't get away from the fact that this is sort of physical reasoning, right? Physical reasoning has to inform this geometry, time scale, and then the pressure scale being sort of the difficult one to get. And I remind myself, I have this acronym, right? What do you want? WDYW. So physical reasoning has to give you these pressure scales, and then it has to be this, what are you looking for, what do you want, what do you care about? The Navier Stokes equations, as we stated them right now, can tell you anything about the flow, but it's almost too general. So you have to decide, right, what are you actually looking for? And that's the hardest part. If you know this, you can just find geometry, time scales, and this pressure scale. You then jump into the scale process or simplifying process. This is sort of where academia lies, right, in this sort of circular iterating over and over again. If I'll make this term small, I'll drop that other term, make that small, consider this thing, right, expand boundary conditions, right. But everything starts from that physical interpretation. And it's not the roughest thing in the world right now because all your, this is being, some physical reasoning. And that comes in with this pressure scale is the difficult part, right? So if you do that differentiation again, remember the fact that what we did is we had pressure scale by this, right? Kinetic energy per unit, per unit mass, per unit volume. So whatever volume I have, I look at the average kinetic energy, let's say, in that system. Not truly average. We haven't done turbulence at all in this class. Okay, and that gives me this relationship right here. But you're only getting that actually because you pick this pressure scale, right? So you could also pick a different pressure scale, right? And this is sort of the viscous pressure scale. So this is, right, you think of this as kinetic energy governs. Right? And then this one has just it's not squared, it's the right? This is a viscous forcing term, right? So this is a viscous pressure scale. Viscous force is dominated. But another way I think about it is sort of right? Frictional loss energy is what's governing, let's say, is one of the governing parts of the flow. Right? If you do it this way, right, if you pick this pressure scale, what will happen is this Reynolds number will now include the pressure. So this is an important property that if I then pick, if I look at the scale of pressure and make it this frictional loss energy, right, I would have the capital dV. And then I would have a 1 over Reynolds, and it's including now the pressure scale. And this gets across a very key property of this idea of what do you want, right? Because these are not, right, these are different because of one problem, right? If I scale now this Reynolds number either to 0 or infinity, I will get different functional forms of the equations, right? As the Reynolds number increases a bunch, what's happening is I just have, right, this one wouldn't make sense. There'd be no pressure left over. Here, right here, it's making sense. If I get it right, if I make this number, if I make Reynolds very, very large, or I have mainly dominated by kinetic energy, limiting Reynolds number to infinity happens is this term will go away, and I'll have the Euler's equations, which model gas flow. This situation, if I say, well, the system's governed by the frictional loss energy, right, or the viscous forces that dissipate between sheets of fluid govern it. Well, making Reynolds number very, very small now means that this term looks like 1, this term looks like 1, and now this is sort of the only term that will matter. It's certainly bigger than 1, so that's the biggest dominating factor for it. So this is going to be something called Stokes flow. This is the nice, right? This is a very nice equation, right? This is totally solvable, actually. So that goes into what do you want? What do you think's happening? What is driving the flow? We're not done yet, because you can even have another less studied one, I think, and that's this, it scaling by the surface tension. All right, so this is an interfacial flows, right? So I scale the pressure by this, and I get another equation. And all this is getting at is, right, there has to be a pressure around to drive the fluid. There has to be one. If there was no gradient pressure, if there was no gradients in pressure, then it would, right, then you wouldn't have a flow. Or if there's no shear forces. So one of these terms has to stick around, which is the issue of this picking a pressure scale. And it comes from where you believe the energy, most of the energy is going or coming from. Right? So instead of surface, and you could actually think of this as sort of, right, this is really a surface energy. Right? And that's the units on that would work out. There's actually a more general case for this one as well, and that's a lubrication approximation. And that's if you scale by so this is a lubrication approximation for the Navier Stokes. Again, a different pressure scale. Now this one I actually lump into this situation. And actually I use this one all the time because, well, this still would compound, right? This would still, when epsilon goes to 1, I get back this. So these are pretty related actually. So I really think there are just 3 pressure scales, being those 3. So in my notes, what I do is I actually just say, well, add them all up, which sometimes is a big no-no. But yeah, I mean, so one way you could then think of, right, you could then take the pressure, and I could just scale as both of them, right? Somewhere in between there. So I could have the average of the 2 pressures and look at what the flow is going to end up being like. So before I was just picking one of them, but there's this idea of multiple scales where you could just say, well, the pressure's maybe somewhere in between there. This retains all the information because, right, if there's very little kinetic energy in the system and really all the energy that's being modeled is the frictional dissipation energy, then the scale would still be there. Likewise, the difference is still going to be there, right? The difference would still pop up too. So if I do the scale that way, what's going down, right? Just really think about that term over there, right? And when you do the non-dimensionalization on the material derivative part, you'll get this u squared, and the h will pop out. So then on this side of this negative, I have here. On the scale, so I have this. And then this popped out a 1 over h as well. So then if I divide out by this, okay, so if I just look at this right? Whatever coefficients left in term parameter-wise here and then here, I'd have this relationship. I still kept this scale of velocity, right? And then divide that out, you'll get this term here. Carry through. So there was a 1 over h on both sides. So these would cancel out. And then I would have 1 scaling like that's 1. Boom. Right. And then you see that's actually a Reynolds number. And you just have an epsilon here. So then this scale now is really a 1 over epsilon Reynolds number and then plus a 1. So sort of an intermediate scale then of this non-dimensional one, where I maybe want to consider both of them, right, is a okay, and now I have a non-dimensional form that can cover most cases, right? If Reynolds number becomes very, very, very large, right, much more larger than this epsilon competing factor, this term goes away, this term goes away. I'm left with the Euler equations that govern gas dynamics. And then separately, when Reynolds number limits to 0, this can be a small number, but it will still be there. And then this operation still has another thing in terms of coordinates. This will still check out. Well, now these terms remain. This epsilon has a tricky thing that happens later on in there. All right? So I actually like that scale, and that's one I use all the time. You don't have to use it. You can jump straight to, well, the physics will be governed by this, so I'm going to use that pressure scale. But I am pointing out when you do this non-dimensionalization that you have to do that initial thought of, what is my pressure scale? What do I want? Is it driven by, right, is this pressure scale going to be driven by kinetic energy, really? Is the energy mostly comprised of just kinetic energy in the system? Is it mostly comprised of just frictional losses? Or is most of the energy in the system going to be on that surface energy? Answers these questions. OK, so now almost there. Now let's get to maybe solving some problems, right? And I have another little picture right here where I go to my 2D flow. Right, remember this flow I had looked like this. It was a sheet. Right? Where there's some pressure in, there's a pressure out here, and you really shouldn't worry about where the pressure is coming from. It could just be from tanks filled with water that have a pressure difference, but there is a pressure defined right here, and there is a pressure defined right here. So essentially, you have a pressure at the point. Sorry. It's in the x direction, right? So we can define a pressure at x equal to 0, all y, z, and t even. And then I can define a pressure here, right? So there are boundary conditions, let's say, on pressure, and they could be very large or very small. That pressure could come from a couple things. It could come from 2 jugs, right? It could come from 2 baths of liquid on both sides of this thing that are at different levels, all right? Or it could come from a peristaltic pump that just assigns a pressure difference across here due to the peristaltic pump going on the outside of the system. But there could be one. If this was on an incline, that pressure difference would come from the difference in pressure from the gravitational field. Because the other end would be lower than the top end, the gravitational field would drive fluid downward, and that's your pressure difference in this situation. Remember in the coordinate system I had here, where this was my downward, and this is z. Okay? So 2D can be interpreted really as this. Right? 2D is when that goes to actually, when this length scale goes to infinity. Right? Or there's no, one way to think of it is that way. The other way is you can just say that there's no, that all the fluid in the y direction just behaves exactly like a bunch of lines going up and down. But there's not a bunch of variation as I look in this w direction. But you can do it with the scale if you just limit the w and all the expressions I have to infinity. You would kill off the z momentum. Okay. If I have time, maybe I'll actually just do that for you. Oh, I don't have that sheet with me. Okay. All right. So lastly, we have these dimensional equations, right? Non-dimensional equations. But I have not assigned any boundary conditions or initial conditions to them. And that's a very important part of any differential equation, is you can certainly just write out the differential equation, but you also need to prescribe things on the boundary. Remember that this, let's say, solid body has a boundary. This is the actual volume of fluid, and then each surface on the edge has a boundary associated to it. The inlet and outlet, let's say, would be assigning values at x equal to 0 and x equal to L. Top and bottom would be assigning values when y is equal to 0 and y is equal to h. Assigning values at w, you don't have them, but let's just say they're symmetrical. Right? So another version of 2D is actually just saying that the velocity in the w direction is equal to 0. This one's a bit stronger because you're saying that there actually is no momentum and there's no pressure difference in this z direction. So the fluid does not actually, my fluid does not traverse and wiggle around this way in this plane, because there's no pressure difference to cause fluid to go that way or this way. The only pressure difference I really have is this driving one in the x direction, either from a scale or you just stating that the z direction velocity is 0. So the boundary conditions we have for Navier Stokes are an interesting one because they come from really experimental fact and observation. And that one being that this is the no-slip condition. So this means that my velocity vector evaluated at the boundary. So let's write out this velocity vector itself. I have a u of x right, so the vector is really this function of scalar velocities, right? Assigning values at this boundary is a bunch of different versions on here, right? And this does not does not care about the time. So you could have, the boundary condition is that that the velocities here and here and here evaluated on the boundary of the surfaces are actually 0 for all time. Right? And there's a bunch of different ones, right? So for assigning this on the boundary, I need to assign it u at 2 different places. It needs to be u equal to when the u and x is equal to 0, and then u when x is equal to L. Same with all of these coordinates. So there's actually a lot of equations lumped up in this statement. But compactly, we say it as the velocity vector evaluated along the boundary. Any part of the boundary, any combination of the boundary must be 0 everywhere. And this really comes from experimental fact. So another one is sort of an addendum is regardless. Because an experimental fact, and we think of it as a physical assumption, right? As a physical law, this no-slip condition is right? It doesn't care about the coordinates that you pick. And that gives you this idea of relative motion to a wall. So if a wall is slipping, right, if that boundary is moving at a velocity, then this statement would go, well, then that boundary has to also move at the velocity. The no-slip condition really is saying if I have this boundary surface where this is a liquid and this is a solid interface. Okay? So what it's saying is if I zoom in very, very, very closely to this situation where I get close to the wall, right, you're going to get if you get so close and you're close enough where there's so much right, attraction between the molecular forces that they don't move the closer you get. Think of molecularly, I mean, it should kind of make sense because, right, molecular forces are a 1 over distance between them relationship. So as it gets very, very, very far away, that force would die off exponentially, or in a power law. But if you get closer and closer and closer, that force of attraction grows extremely large, right, limiting down to when your assumption that the fluid was a continuum fails, which is fine. Then you get when you get molecular gas dynamic flows, we have to use like a Lattice-Boltzmann method, but we don't care about that yet. But it makes sense that you should think about this. I used to have issues believing that because it would seem like, what do you mean it's not moving at the boundary, right? But my favorite example of this is if you look at your fan. I guess if you sleep with a fan on, maybe you have this box fan, or even the fan in your house. Look at the blades on that fan, and if you haven't cleaned it in a while, you will see a ton, right? You'll see a lot of particles just all over it. It'll be really dusty. Also means you should probably clean your fan, right? But if you're really lazy and you haven't gotten around to it. So the no-slip, so you can even see the no-slip condition, right? Because on your fan blades, there are these particles of dust, right? Here's the surface, and like you really kind of have this particle of dust right here and here and here. So the velocity of the fluid, as you get down and down to the surface right there, that particle would move if there was velocity right there. But it's not moving. So you can almost think that, right, you can see the no-slip condition on your fan blade. I also remember the no-slip condition and believe it a lot because if any of you fish, you always know, right, sometimes you have to cast out to like the lower end of the stream where the fish are eating, and they'll hang out the bottom of a stream, right? So here's your river, right? Fish will hang out down here, and then bugs will float down around sort of near the top of it, really sometimes the surface. But if they're dead or they're struggling for their life, they'll sink down here. And what a fish will do is it'll jump up from when there's no velocity so it can conserve its energy, and then hop up and eat its bug. Right? So I also think of the no-slip condition as a nice condition because it lets fish conserve their energy when they're down at the bottom of the creek, and then they just hang out there because the velocity profile here we'll see looks like this. Right? So this means low velocity. Low velocity by the no-slip condition, right? So if I hang out down here, because of no-slip condition existing, I can not experience as much drag, not exert as much energy, and just wait for my food to come. I'll just hop up, eat the bug, then come back down. Hop up, eat the bug, then come back down. So it's even a mechanism people will use, this no-slip condition, physically. But for us, it's a mathematical statement, and it gives us something to always assign for my general equation. I'll always assign the no-slip condition. Okay? And then finally, so I want to say this, the BC. These are boundary conditions. And then finally, we'll also need some initial conditions. Now, what's the initial condition? Well, the initial condition is you have to start your simulation at some time, right? So usually this refers to time equal to 0. So what this is assigning the vector field everywhere, right? So this initial condition a vector field naught. So the initial condition, what it does is you say, starting my simulation or starting my model, what I'm going to assign is an initial velocity vector field, right? Because this being 0 means I can still vary from my x, my y, my z. So this condition means if you have your region of fluid, right, where these are the boundaries, and you assign velocities there, they're given by the no-slip condition, the one arbitrary thing left over, right? Think about this. Pressure, we've kind of taken the arbitrariness out of it by going like, well, I'll measure the kinetic energy source, the frictional energy source. You can even add the surface tension energy force in there. So you've counted up energies, so you've maybe taken that out. But what I can't take out is now this. That is general and up to what your problem says. Yeah, I can't make a natural velocity scale, right? This is up to you in some sort of scale of, right, and just some sort of problem that you're posed with and given with, right? So right here, the V naught, think of it as actually assigning the position and size of all of these vectors, right, at every point in space at some time. So that's, right, that's the difficult thing. And then, really then, you could actually, right, if you then, considering something like that, this initial condition is what gives you velocity scales. And that's an important conclusion because, again, and that's sort of the circular part of this whole process of really analyzing fluids, is you have to assign this, right? So you start off with some arbitrary state of the velocity field, and that being the initial condition. This is taken care of with boundary conditions, right? Even if I have a shearing force on the top, I could still grab a velocity out of there. But when it comes to this, all up to you. So your velocity scales, let's say if I wanted to have a u naught and a v naught, what are then all these scales? Well, if you did assign, if you are assigning a velocity field at the initial time equals 0, that's where we can get the scales from. Because if this is a vector field, right, this would then just be, right, right? So now the scale would be, you look at your initial condition, you do some maybe a numerical integration or just like consider it in general. That would be your scale in the U, your scale in the V, and your scale in the W. But you have a way to get it always because you have to assign this to have a fully defined problem. So when I said I love the Navier Stokes equations, really my muse are these things right here. Because I don't really deal with compressible flow, and I don't really look at the energy equation, and I maybe should. That's maybe why I'm, whatever. So these are the things that I obsess over and keep up at night about. And this idea of selecting these velocity scales is impressive. And even there's a combined thing, right? I mean, if you did have this vector now, right? So now, if you have now these scales that come from some integration over all of your vector fields and taking the averages of them, okay, now I would have these. These are scalar numbers, and this is a vector. So you could even, right, maybe even a better scale would be something like this, right? What's the magnitude of your scale vector? Also a fairly good one. Right, because you can see already, right, if you did have no velocity in the W, or it's fairly small, right, you would play the exact same trick I did with that operator of the non-dimensional gradient. And you would then look at ratios of scale velocities. So now if W is really, really small, 2D, that would drop out in your momentum equations. The v velocity might not be known, but you could figure it out. But again, if it's very, very small or constant value, you could figure it out. Okay. So I'm going to change the website, actually, because I'm looking at my time, and I'm not going to make it. So what I'm going to do is, you might notice a change. I'm going to make this a two-part. I'll make this a two-part, right? Haha, simple flows. Why is it two parts? But I'm going to drop the compressible problem. Dropping the compressible problem, and I'll make this 2 because now I have everything kind of set up in a very well preconditioned solve my problem, and now I want to sort of rattle off types of solutions and what we can get. So I'm just going to focus totally on incompressible, no more compressible in the class. Sorry. And also, nobody in the term cared about the high velocity flow stuff. The project's going to be on, we considered that Helly-Shaw flow with a porous media structure in space, so that has nothing to do with compressibility. So how about we just forget about compressible flow, and I'll make this a 2-part so I can really slowly go through all these processes. Again, I've modeled this lecture right now on the idea that we have no idea how to solve that 2D parallel plate flow. And you're just starting from just scales of geometry and you're going to get somewhere. So it's taking me longer, but I think it's important maybe to just see how the process of this stuff can help you. Again, I've said nothing. I have said nothing about the differential equations that are simplified. All I have made mention to so far is non-dimensionalization. Really, all I've said is my plate's this wide, this long, and this tall. So hopefully you see a type of power in there. And pressure scales are important. And then this velocity initial condition is important as well. OK. So back to our concept, right? What I said was I'm going to make W go out to infinity, right? And that informs me that it's a 2D problem. OK? So now I have this situation here, because there's no change in and out of the board. Here's y, and this will be my x direction, again, in coordinate system. OK? And now, with that operator, remember, I erased it, right? Remember how I defined, right, this, right, the definition of this thing, or really sort of, this could be defined as or really, like, if you after you end up doing it, I just write it like this, right? Okay, so write this down. Right, my assumption that the y coordinate was really small, and my definition of how to define this non-dimensional gradient operator gives me this relationship with epsilons. So, right, this epsilon really is an epsilon prime because this one right here really kind of, right, this epsilon prime looked like an h over w, let's say. So that's actually an even smaller version than the rest of them. So this idea right here, you can even say that this is even more negligible. So, in fact, actually, that was the step I did there where I had this L over m being much less than 1. Maybe it's equal to an epsilon. Then I even had the further constriction that this is actually less than 1 as well. Well, that can be informed as like, that actually makes this an epsilon squared term. So now all of your z momentum equations are 2 orders of magnitude less important than the ones prior, right? And then you get to the situation here, right? And this is that concept of entrance length, right? So I can make this 2 orders magnitude less, but I still retain this 1 epsilon. So if L is long enough, right, if I really make it go to 0, this will die off and I get my one-dimensional problem. So let's kind of analyze this idea of continuity without the z momentum equation. Okay, this is just looking at the continuity equation, this fantastically small equation. And one trick I remember always or I forget who told me this once, and I never forgot it, and that is the rule or idea that sort of reminding myself that the continuity equation is a way to help determine is a way to determine the relationship between velocities in your problem. All right? So this term right here is encapsulating really this entrance length situation. Okay, right? And you would see this as an exercise if you looked at the way I wrote that with this 1 over epsilon term. Right? So I had a 1 over epsilon Reynolds, and then I had this pressure, and then I would have this 1 over Reynolds velocity. So there's some constriction on when you can say this is 0, and it's based on a Reynolds number relationship. Right? From undergrad, maybe you just saw these relationships that the entrance length really was right. It was proportional to, it was a function of Reynolds number. You can go look it up, what it was, but that's important that you could calculate what this entrance length was to the region of flow you had. It was a function of Reynolds number. And that comes out from this relationship if I had this epsilon competing with the Reynolds number in the pressure scale versus the curvature in the velocity scales. It's kind of fun. But again, in the pipe flow, maybe you remember the situation if I have a long cylindrical pipe. Again, if you're doing this at home in cylindrical versions, you'll see that the y coordinate ends up being your r coordinate. Right? And then this x coordinate is really the z coordinate. And then the swirl velocity fell out because you said there's symmetry or there's no swirl velocity in your tube. All right, so maybe you would see that, right, you had this concept where right here there was a point when the velocity gradient was non-zero, maybe there's a transition region, and then you had kind of past here the velocity gradient was equal to 0 past a certain point, this point being an entrance regime. So you had the situation where flow went in, I had developing velocity gradients, but eventually the velocity profile just looked exactly the same no matter where I looked at it. And that's this. If this is the x-coordinate, this relationship where after a certain time when the pressure has where the pressure has come to a constant relationship, we can actually derive that, there can't be a change in the velocity profile as a function of x. Other ways to interpret this is if you have a graph of x and of pressure, right? Pressure coming in, let's say, directly to my pipe, there has to be some connection region right here, right? Let's say is very high, and I know that pressure at the end is very low. Right? Because there wouldn't be a flow through my pipe if I didn't have high pressure at the inlet and low pressure at the outlet. It drives the flow. What happens here is there's like some curvature happening, however it is. It's not a nice function. And then you see that after a certain point, it just looks like a line. So there's an adjustment phase. There's an adjustment period right here. And then you get to this. You even measure this as a constant. Right? And this adjustment in pressure of going from extremely high shear forces at the wall, right, and then decaying down to a constant pressure gradient is this entrance regime. And that entrance regime can be calculated, and that entrance regime is really this balance between the length scale and the Reynolds number. So it's a balance between I have all this kinetic energy moving in, and I'm now converting it to really the frictional loss energy. So that transition takes an amount of time. Time is proportional to velocity, and that happens right here. Past that point, you get no change, and you don't get a change you don't get a change in the velocity profile as a function of x, right? Another way you can really, right, so another way about this is that is a way to help you conclude that this has to be 0. So epsilon could not be 0, but then this would be 0 after a certain point. So that's one equation. What do we get next? Okay, continuity, right? So then the y momentum ends up being this. So this is my y, right? Continuity goes into here, kills that. Based on the epsilon being so small, it doesn't matter. Okay, continuity goes in there, kills it, and now what I have is a relationship with the pressure in the y direction. So now I have some information about how pressure varies from the bottom of the plate to the top of the plate. So you can go ahead and actually solve this equation. Okay, and this, if you integrate it, right, you'll have that the non-dimensional pressure right? And this is your extra integration constant that would come from that pressure. What is it telling you? It's telling you that the only pressure difference that happens in this plate of a flat plate up top and a flat plate below is just the gravitational pressure difference. Right? All this is saying is that no matter where, right, if I go down a certain level here, this is just going to be rho g, right, h1. If I go down here, that pressure there will be a rho g h2. More important, right, and then importantly, the question is, right over here, though, there can't be, right over here, there's some addition of a pressure term right here. This is not rho g h2, but it has to be rho g h plus something, or else there wouldn't be a flow happening. And that's what's right here. That's the additional part. So anywhere on one level of non-dimensional y equaling a value, it will have this gauge of here. It will have this gauge pressure just being the gravitational pressure that exists, right? Thermodynamic property happening. But there's this extra part, right, that's encapsulated in this F term right here. Good, so we're on our way. We know that we at least know this form of the pressure function, or P star. On our way. What next? Okay, so now the all-important x momentum equation, right? What do we end up getting? Maybe you haven't seen this version before, but one term actually will retain itself because of my 1 over epsilon term. I mean, extra credit actually is, I mean, really extra credit is sort of do all of this stuff. Right. There's actually a Reynolds number left over here. But if I didn't have, okay, so then I have this 1 over Reynolds number here. Yeah, so then sorry, I want to just have it. Why am I doing that? Why am I doing that? Stop. P star, P x star, and I have this. Okay, these are just what's left over after I've done my after I've used my gradient star operator. Right. Yes, this is x momentum. So so we can do a boundary condition for this left-hand side. And this left-hand side actually will only hang around if my Reynolds number, right, is a dominating term. That's also important. This is because I picked up an epsilon from the non-dimensional gradient operator. I picked up the gradient non-dimensional operator. The epsilon multiplied through. I get this tiny number right here, 1 over epsilon, so it canceled out. So I left this pressure gradient, so there's still a driving pressure flow right here. And then I have this leftover term where there's no epsilon, right? Remember, in this non-gradient term, in this non-dimensional form, there's no tiny term I can limit to 0 in terms of this dimensions. It's an order 1 operation. So this term sticks around. Okay. Again, you might be able to see, you can kind of see this issue of when is the epsilon actually 0 for that entrance length. It comes up right here, right? Because there's there's going to be some amount of Reynolds number where this is too large to make any sense. And then it's just going to be driven like this. And then you get sort of bad physics as well because you haven't done the turbulent regimes. But, okay, let's just say all the assumptions are holding right now. So this goes down to 0. This goes down to 0. I'd be left with this, right? And I'm actually going to move it over to the other side. So I'm kind of just left with my order terms. And now this term is something that you maybe have never seen popped up in this problem before. But it's interesting if you do it in this formulation, you see already that there is a situation where you could retain this in a small approximation. So this term will stick around in something called an asymptotic suction flow. Okay? But for our formulation, we can get rid of it with a boundary condition. How do I get rid of it with a boundary condition? Well, this situation right here, right? This tells me that V star has to be some constant value. All right? So if I have no flow going up this way, so how would you have asymptotic suction right now? You could have this could be a very porous membrane, let's say, and you have a bath of dye in the bottom, and you apply a suction at the very top, but not that intensive a suction. So that would be giving you an extra pressure gradient happening here that we never talked about. But that would then have a pressure gradient across here, and let's say be a very tiny one. And this would be let's say, dye flowing through this 2D slot. So again, this could be very porous, and this could be very porous. So porous that you could treat it like a solid wall. But you could apply some small suction such that dye would, let's say, smoothly kind of flow into the flow, right? Smoothly kind of flow upward to try to get up to here where there's a lower pressure. That would be asymptotic suction flow. And you see the term pop up right here, right? And the asymptotic suction flow only arises because of a boundary condition, right? Because, right, I could then set this suction flow to be very tiny, and I would then say, all right then, so I'll now assign V prime at 0 to be, let's say, a V naught, Vs, a suction flow, let's say. And then non-dimensionally, I'm still scaling by my non-dimensional velocity. And you really just need this to be a very, very tiny term as well. And that's important because then this is an asymptotic term that you can add on to the U part. It will fail if it's too large because then you would have, right, because if you have a lot of pressure gradient here and a lot of pressure gradient here, you would get vorticities and swirl happening. But if it's very, very small, you can get these asymptotic suction flow, which comes up in this process right here. What does that also infer? This also infers, since this is a constant, my boundary condition assigns it as a small number, it has to be that throughout the entire velocity field, right? So continuity told us, right, up to epsilon being 0, this term velocity in this direction must be a constant. A boundary condition assigns it to be some number, and what that means is since the solution of this then is just a constant value, right? That means v at 1 is, let's say, an epsilon, a v at, right? So everywhere along here, it'd be the same velocity in the upward velocity. That's cross section. All right then. So, but if we assign the boundary condition, well, I have no section, that then kills this term by a boundary condition. BC1. Now I'm left with just this governing equation. Okay? I had a boundary condition for my v velocity as well that was making it very small. But now I'm left with this. Okay, importantly, now what do we have here to say? I need one more. This is where I actually need to be able to conclude. I need actually this now, because I then have a conclusion here. Okay? U, if I don't have this, could be a function of x and of y, because it's all that's left. Steady state. Back up. We're going steady state on this problem. But this conclusion, the fully developed conclusion, means that the function is not that the function is not a function of x at all. So this is saying, well, then I know that y can only be a function of y. At steady state. So that's where the fully developed one comes in. Because with that, you then do this little trickery right here, where you say, this then is only a function of y. This is a function of x. Why is it a function of x? Because of the y momentum equation, all I got after epsilon terms was this. So if I take the gradient of the respect with x, this goes away. I'm only left with this term, which is only a function of x prime. Okay, and now the only way this would work, right, because this is a differential equation, right, I would have this on the, right, now that I'd put this then on the other side. Okay, if I integrated this twice and I want to recover only a function of y, that means, right, and that's classically this sort of shown relationship, that this has to be a constant. That's already, right, I have seen that picture of the flow developing through a pipe so many times, and I've been told that, well, there's a constant slope. And I just went with it for the longest time, like, okay. Right? I saw the picture many, many times, but this, I forget where I first saw this, but that's like, thank you. Thank you for somebody telling me why on earth I just draw this linear decay of pressure. It's a consistency thing that you're saying. It's a consistency thing of the velocity profile, given all the assumptions that it's the same inside and outside, right? That I have parallel flow, and it's a consistency thing of this fully developed conclusion, that my velocity profile no longer changes as a function of x, because I'm in some good regime. I'm in some good Reynolds regime, right? That's the key. And then from that, you make this. You can actually tell yourself, aha, the pressure gradient has to be a constant value. All you could tell from the momentum right here was that there is some varying part in terms of x. Combining this with the momentum equation is what tells you that, oh, this is a function. It's just a really boring function. It's just a constant function, right? So for all this stuff to, right, for all this stuff to be satisfied, right, this has to be some constant function. And when would it not be satisfied? Well, it's not going to be satisfied if epsilon didn't really go to 0, i.e. my length scale down the pipe is going shorter and shorter and shorter. So if this L that I've talked about here is getting smaller and smaller and smaller, well, I'm getting less and less obvious that the epsilon is actually 0. So I have to then keep it around, and I can't say this. And that, right, so then that's then when you'd have a situation where you have to then model entrance effects. How do you think someone would model an entrance effect now? Well, they'd probably do some sort of a correction asymptotic thing. So we're almost there, right? And this is sort of the tease I'm going to say, because I'm just going to really set this problem up, right? Because now we've gotten now to this extremely general problem that we have, where if everything I've talked about is satisfied, this is the governing system. A very simple differential equation. It's actually an ODE. Okay? Now, what are my boundary conditions? Well, so what do we have? We have the condition of no slip at the base, equaling 0. And what condition do I have at the top of the plate? So the top of the plate could be also 0 as well, but actually what I'm going to do is I'm going to actually allow it to be some velocity, actually. So in the problem that we had this parallel plate flow, right? But really a more general boundary condition is that you allow some shear to be happening at the top of the flow. So I already have a good enough generalized problem of this 2D type flow, and I've gone in it from just pure scales. This is really my last trick I'm going to do for this problem setup, right? And the trick being that, well, I could have a solid boundary right here, right? But that solid boundary with a pressure gradient, I could also be shifting that plate, right? So this is a situation where you'd have some, right? And it doesn't make sense with the 2D parallel problem that I have right here. But if you've done the radial problem, right, if you've done all this non-optimization from like first principles, right, you have the case where, well, this is basically your r coordinate. X turns out to be your like z or down pipe, a down pipe coordinate, right? We make this change. Right? And then this theta is the z coordinate. And this doesn't matter. And it doesn't matter because you're saying there's no swirl. Right? So this problem, right, if I did it in radial, I would have a very good model, let's say, of a pipe with almost, let's say, another pipe in there, right? Or actually, I could even have a wire, let's say, in the middle, where I have a very, very tiny radial thing. It's one little trick that is sort of left. So I could have this situation where I have no slip here, and maybe you have this pulling of the outer sheath or tube, where you have these two cylinders translating over each other. Well, close to the surface of one of them, right? Now you can actually solve, you can have the same problem and have this annulus differential equation that I could maybe do. But the problem setup is still the exact same, you just have different conditions. So you could have this situation, and this idea of having an exterior velocity could be a situation where I'm pulling the sheath out, and I have a pressure gradient somewhere across it. Or another one I like to think about is really a sort of a lie, and really a basic approximation. But you could have this idea that I don't know if any of you fish, but So I have the top of a river, right? And then down at the bottom, right, I have surface effects. Right, so I have an interaction between surface energy and viscous energy. So then right here, right, there's some sort of region. I'm almost done with this problem setup. I mean, really, we're done with the problem setup. So right here in this, let's say still, not even a river. I don't want it moving. Really a lake. Okay. So right here in the lake, there's some region where the surface of the lake, it affects penetrate through all the way down somewhere, some length dimension dependent on this surface effect. Really what that's saying momentum-wise is the velocity field around here is definitely not zero. Terms matter. And then maybe there's an intermediate part if it's deep enough, right, where the currents aren't strong enough at all. Or part of the lake, it really is zero velocity field. It's just still, maybe it's a nice summer day and you have still liquid. There's no, the winds aren't that strong. Currents haven't gotten that strong ahead, but there is a temperature gradient, let's say, happening. So then maybe there's a region somewhere in here where it doesn't really quite matter. I'm only saying this so I can ignore this surface effect right here. Again, this is sort of this very rough approximation world I'm saying, because I'm trying to now put my stupid math problem into something I could maybe use one day to say something about something. So I have this region here where the material derivative velocity field is not zero. I had to consider some things, and that's the effect of the surface tension. Here, there's no interface, right? It's just pure fluid right now, so that effect doesn't matter. And maybe it just doesn't look that motiony in this area right here. Okay? And then I could get to this point, right, where I have maybe some undercurrents happening. Right, some eddies, or maybe there's a temperature variation in here, right? Maybe some shift or something like that. But then maybe you get deep enough, right, where you get back to a situation where this is definitely not zero, right? And this being not zero is not due to a surface effect. It's going to be due to interior currents, let's say, or motions of the fluid. And now, right, this idea now of some shearing motion happening right here. If I did have some sort of little fish down here, I'm happy, right? And there could be a motion like this kind of right above him. Maybe there's a surface right here of some shearing force happening. Well, up around here, this would almost look like my infinite velocity right down there. And I'm trying to look kind of close to this fish, to the fish's scales, and see what kind of energy he has to care about. So how far deeper does he want to go? And that's kind of this problem, right? Because if that motion's moving around, he's just standing quite still. Well, I know there's no slip on his little fish scales, and there's an upper current right here. So it's almost maybe kind of like this problem. So you need a pressure gradient due to a temperature difference. But OK, this is just a game I play with myself. OK? All fluids problems with non-dimensional, people get them down into just like nice, concise statements. Right? This is the problem. The real challenge is coming up maybe with somehow you can apply that simple problem, right, to some, just gut feeling of what does it model in the real world. So I have my little fish examples because I think about fish a lot. But this is an amazing result that we got of the 2D. Okay? I'm out of time, so next time we'll actually do the integrations and we can look at different scales. But I think this is a nice place to stop because of one maybe overarching or a whole class. I kind of want to get this across. What did I do? Right? All I did was I talked about dimensions of my problem. All I did was that. I just said H is big, L is very big, and W is big, because I can do that, I can measure that. I have no idea what this velocity profile is going to look like. But I could make measurements, and my dumb human brain can only think of so much. But what I did was I talked about scales like that. And then really what I did was I reduced the Navier Stokes equations. Okay? That's all I did with some scales involved. And the idea is I reduced them to a very simple system, a very simple ODE. With some boundary conditions. Right? That's it. And that's really the solution. Because we live in 2020 now. You have Mathematica. You have, I'm not one of those professors like, well, you don't have a calculator. What do you, like, we have calculators. We have very good symbolic calculators. We have good numeric calculators. So the solution analytically is this. Right? Writing the governing equation, right? Writing down. Right? So I want you to get away from this. I stopped here because even in my brain, if I do a fluids problem, if I can get to this point when I write down a very simple ODE or even PDE, I go, woohoo! I won. Because now it's just the fact of marks on paper or clickety-clacks on a keyboard. Somewhat, right? I mean, homework 1 is this issue. But you got somewhere, right? I mean, if you're just an analyst, you at least got like, and the governing equations for this fluid problem is this. And you say that, and then you let someone else do the numerics if it's really, really rough and tough. But for us as humans, this is all we have left. All we have left in fluids is to reduce the Navier Stokes equation to simple ODEs or PDEs with boundary conditions and initial conditions. That's all you have over a computer. Now the computer can solve this. Or you can do it analytically, right? You can look it up. Right? Look up. You can look it up. You can use the computer. Whatever. I don't care. But maybe making that shift mentally, where the shift mentally being my solution is the governing equations of a system that came from the Navier Stokes equations. I just did some brain thought to reduce it down to a simpler set of equations, which could maybe be solved in a more easier fashion. A computer can't do that. You know, I'm on total soapbox time right now, but what a computer cannot do, right, is you have to tell that computer, don't calculate the z momentum equation. You have to tell that computer, right, that it's incompressible because I say so. You have to tell that computer to not compute these terms of the equations. It's just going to do whatever you tell it to do. Right? So one of my buddies that does a lot of CFD, he has this funny joke that I love. It says, the form of purgatory for somebody that performs CFD all their life is to sit in hell and compute all of the negligible order equations they made their computers make their whole career. Maybe no one laughed at that, but I think it's funny that if you do CFD, you can feel a little bad for your computer having to calculate, 0.001 terms. It doesn't really have to, but you're making the poor thing do it. Okay? So differential equations are solutions. Simple. Get that out of here. That is so big and changes your perspective as someone that uses their brain and math to make statements about things. That getting to the idea the differential equation is the solution. Now maybe we'll stop there. After that part, it's done. You can go ahead and even calculate this. It's like really not that bad. You even have these velocity scales. Up next lecture, I'll solve it and go to the point, and I'll solve it, and I'll actually get to a situation where I actually never had a velocity scale that I defined, and then you can get some parameters based on that. Okay? But what do we learn? What do we learn? We learn if you have no idea what to do, you could draw your problem out really well, right? You could really define this capital omega in a very specific way. And then you can do all of this scaling stuff. Really start from here in this class. Right? These will keep you up at night. These are the non-dimensional Navier Stokes equations for an incompressible flow. Right? They're the best. Right? You can think about them for the rest of your life. And assigning then, right, this idea of then assigning how the non-dimensional gradient operator behaves, how the non-dimensional velocities behave, give you then a structured way to simplify down the Navier Stokes equations. So in this advanced class, we're no longer just going to have problem statements, I believe, going like, imagine the fluid flow is only a function of y and t. No, tell me why it's a function of y and t. And you do it through just scales of velocities. And you get very simple differential equations, whether they be ODEs or PDEs. But your solution should be really thought of as defining a simple ODE with initial conditions or boundary conditions, or a simple PDE with initial conditions and boundary conditions. That is our role as humans in fluid analysis, if we're not doing the computer stuff. That's what we can do. We can show the computers what's up by doing this stuff, where we use our brains and go, I know what matters in this equation, I know it doesn't matter. So that's my little soapbox. Up next, I'm just going to roll through a bunch of these simple solutions, and you'll see how powerful this statement is. You'll see how powerful and how many equations you can get from this. Hope you all like the new camera. And check back next time when we do the solutions. There's no compressible flow lecture anymore. I'm just going to run with this for 2 lectures. So hope you dig.
Yeah. Can't train. Came by the trap, if I fall off, I can do the same thing. Rap game, face all over these magazines, I can't slang things. Insane, but he rabbit game, throw it down for the set. VV, when you see me, hold these double G's, got my neck wet. Anybody killer hitting all crews. Crack was moving slow, I move the dog food. Nigga for the law, breaking all rules. Mr. Petty Whopper with the dog food. Lost a couple ounces, that's a small move. Pull the 50s out, we bringing all tools. Get a truck and fill it up with all goons. When the crack was slow, I move the dog food, nigga. Bitches, young Coleone, soprano, baby Tony. Straight out that east side, my breakfast was eggs and fried bologna. Can't politic if you neutral, I fuck with members only. I pulled up that face with choppers, bitch, I ain't sitting at home. Fuck niggas getting sprayed down, yellow tape and stretcher getting laid down. Call my nigga black and get some cake round. Yo, this been my nigga since the playground. Yo, this been my nigga since the sandbox. Pour run the turf, I got the landlock. Put it in the pot and made the grand fly. We was out here surfing, had the hand rocks, nigga. Can't train, came out the trap, if I fall off, I can do the same thing. Rap game, face all over these magazines, I can't slang things. Insane, bunny rabbit gang, throw it down for the set. VVs, when you see me, all these double G's, got my neck wet. And my money roll, it do not fold. Got a roadie Daytona's all go. Politic with Pablo's chopos. I don't got a minute, but he dog codes. Bitch, I never been, I do not fold. They was on the Chevy, they was all gold. Politic with Pablo's chopos. I ain't got a minute, but he dog codes, nigga. Yeah. Politic with Pablo's chopos. I ain't got a minute, but he dog codes, nigga.